converted into images. So now I can't do anything with it. And I really cannot go back to the previous one either because I don't know what has changed. So the original was like this. So the docx format was like this. So I thought, okay, I need to make a stopping to this. I need to stop this happening. I need to send him an email and explain what's going on. And I said, how are you? Sorry for my late reply, usual stuff. And then I said, I started the whole work on LaTeX because Word is causing a bit too much of a trouble for formula. I attached both the PDF and the text files. Feel free to comment on either. So what is my hope here? My hope is that he will be saying, oh great, we've got a text file, we can work together. So what is the response that I get? Thanks, but we've got a problem. I don't work on LaTeX. What do we do now? So now I'm just like all desperate and I don't know what to do because there's no way we can work these formulas. There's really no other way. And this is happening this year, March, by the way. And this person is a statistician. So I'm not just saying this is, I mean, I couldn't find a solution to this problem at all. I said, okay, I'm going to work on it. Don't worry. You just type your whatever you want to type, I'll convert it. So I've dedicated myself into editing the file based on his comments. Okay, so that was one thing. So here is something I found on the internet, which I think some of you might have done this. So retest that, WTF that. Use this one that, so you don't know how to name your file. So this is quite a hilarious example from my point of view. Okay, so this was an example from myself and my collaborator, but you as a researcher, you're a student, you're going to now start writing your manuscript and send it to your professor or whatever, and the professor will send final revision comments, corrections, and then final grade 22. This actually does happen. It sounds funny, but unfortunately it does happen, and it did happen to me as well. Okay. So this could happen at a company. You might be going to start it at a new company, or you might be starting with someone and they say that, don't worry, I've got all the code. But then there's nothing actually explanatory in the code. Everything is like a command that you need to get through, you need to read through, so there's nothing information. You would be probably better off writing the whole code yourself. Okay, so here is a very recent research of mine. This is just an R code, and I have done data original missing, original 2017 no missing. Okay, I don't know what this no missing means really. Now I do know, obviously it has been 2 weeks since I worked on this, but you can imagine 6 months later, I won't remember what I've done with this no missing thing. Did I delete the missing data? Did I impute the missing data? So I don't know, and I haven't written much there. So you can see the problems that we are coming to. Here is a research paper of mine with another Turkish colleague. And at the time, 2017, we decided that's a very good idea to put the data on our, I'm from Istanbul University as well, by the way. So Istanbul University at the time, they had a web page for every lecture. Okay, we said, all right, we're going to put it there. But years later, Istanbul University decided to close all those websites, and we were left with nothing, but this journal article was published, and it is all there. And if you go to that website, you will see that this site cannot be reached. Okay, that's dramatic, I think, from my point of view. Okay, so as you can see, for many people, all of these are a problem. As a researcher, it's a problem. Your collaborator, it's a problem. If you're an instructor, if you're a lecturer, it's also a problem. So you get in front of the students and you start going through your code. You don't know, oh, actually, I don't know what I've done with it. So that is a disaster. So in order to prevent this happening, we need reproducible research. And it can be reproducible lecture. You can say anything to that. So I'm just going to skip these because we all know what science is, what we do is, what is replicated or replicable research is. and why we need reproducible research is more important for me. Okay. So replication, you can replicate your research problem, but then not everything is replicable. So as a result, we need something in the middle. We can't actually sit down and start crying and say, no, we can't do anything. We need to be able to do something, which is the replicable research. So what are the advantages of the reproducible research? You get better work habits, better teamwork, changes are easier, higher research impact. So when I started university, it was 1996. Then I had to write a report. What I did is click on the program that gives me the result, copy and paste every individual parameter estimate to the Word document by hand. So this is not going to happen in this world of the data that we have. We will be repeating all of our research many times, change one data value or add another value, which is quite happening, so you get lots of data being added onto your data. You can't actually waste your time by copying and pasting. You need to be able to make the changes easier and faster and create a higher research impact. So what tools can we use for reproducible research? Can you guess what I would be talking about? I'm a statistical sciences person, stats person. Which tools do you think I'll be using?
R.
Yes, that's great. Yes, that is R. But none of this. I'm not claiming that all of this can be only done in R. It can be done in any other, like Python. You can use the IPython. You can use MATLAB, or you can use. If you're a Stata person, you can use a do file and so on. Okay, so before explaining the tools, I'll go through very quickly obviously the life cycle of a research. If you're a statistician, is you collect your data, you clean your data, you do some statistical analysis, and you need to present your results either as an article or a conference paper, or to your other collaborators if you're collaborating with the industry. So for every step you need a reproducible research tool to do all of these things. So I can give you some tips. Do document everything. Do write down everything that you have been doing. So before becoming an academic, I worked at a company for 8 months. It was an insurance company. It was back in 2001, and there I actually experienced the computer department person, who was a research analyst. She was writing every single change that she was actually doing to a research document. So it was actually done by them, but she wasn't doing it on a systematic manner like the way I will talk now as a researcher. So all files should be human readable. Whenever, obviously, you're writing a code. What is the code for? The code is for the machine to read your code. You tell the machine to do something. That's the code. But you need to be able to read that as well. You need to be able to understand what that piece of code is doing. And explicitly tie your files together. So that is something that I come across with myself quite often, because I like to sit down in front of my computer and change the name of the folders and change the name of the files. And then, unfortunately, in an R code, one of the data is coming from X folder, and that X folder is not existing anymore. So you need to be able to explicitly tie your files together, your codes and your data, and have a plan to organize, store, and make your files available. So what are the tools that you can use for that? So the tools that you can use, okay, I'm going to skip that. The tools are, you can use R, and you can use RStudio. RStudio is just a user-friendly interface environment, and you can convert your codes into a LaTeX file as well. But in order to do that, I think MIIA is a really, really nice package. And you can write down as if you're writing, you don't need to do the LaTeX begin document, end document, begin frame, end frame. You don't need to do any of that. You just need to do a hashtag, and that's it. That creates a frame for you. So it's quite easy. You can find these, and the R Markdown. I will talk about the R Markdown, the file of this in my GitHub site as well. You can play around with it. And what is R Markdown? It's one of the document formats that NetR supports, which is a language. It's a Markdown language, and it's very easy to read and write. So the purpose here is you need to be able to read your document easily, and someone else who is reading it can read the file easily and edit it easily, which is R Markdown is for. Cloud storage and versioning. So you can use Dropbox, you can use Git or GitHub to store your data, your code, and your documents and everything. You can create your own website even with the GitHub. You can look at people's websites. And this is more like if you have large research projects, you have cloud computing, so you may want to write a code, but you don't want to run the whole code. You might want to run bits of the code because it's taking a huge amount of time. And then you may want to use the net files or Unix like shell programs. Okay, so NetR Markdown. I actually will leave it here. I don't want to take too much of the time because it's getting late. If you have any questions, please do ask. I can actually show you just the R Markdown that I have here. Oops, maybe I shouldn't have done that. Oh, there is R Studio. That's perfect. Okay, so this is the so you just give a title, this is an R Markdown, and all you do is you use the NetR package, and then you just convert it into either HTML if you want to. You can convert it into a PDF article format. You can convert it into a Beamer. All you need to do is just change this output here to HTML, or do just say PDF article. You can put in preamble. You can say, okay, I'm going to submit this article to Biostats. I think Biostats Journal is actually requiring you to provide your files onto GitHub and the R Markdown. So you can just use their preamble so that it becomes like a Biostats article. So everything, the preamble or the pre-defining is happening in between 3 dashes, there and there. And then you start your document, and you can see I'm actually just not adding any tech comments or anything. It just converts it into a text file for myself. And you can say that I want to keep the text files. You can say keep text true, and it creates this text file for you. I didn't need to write any of this document class. Use package, I didn't need to do that. It has been done from R Markdown with NetR for me automatically. So you can see that this is quite a useful thing to do. All you need to remember is from today, from this evening, please do comment on all of your code. Please do document everything. Do write down what you have done with any data or any analysis. Why you're doing that analysis. Then when you get back, you could be you who's forgetting what you have done, or it could be someone else who's going to look at it, so life will be easy for them. All right. Thank you. This is available. Going back to my CPA.
Get up.
Okay.
Oh, go ahead.
Just shake my mind.
Good stuff. Thanks, Sebnem. We're also going to make this presentation available on the Machine Intelligence Africa website, machineintelligenceafrica.org, if you go there. So thank you very much. Any questions? Quick question, one question. Yep, here we go.
I would like to know that can you do the same thing in Sage or Python?
Yes.
Absolutely.
You can use the notebooks, Python notebooks, you can indeed. Yes. That's quite popular at the moment.
Without using the markdown so that I can create the PDF from the Python.
Yeah, so as far as I know, yes, you can, but I haven't worked with it because I'm not a Python person, I'm afraid. Worthwhile experiencing or exploring the area, I would say. Yes.
Just on that, you can. So if you export directly from the Jupyter Notebook, it doesn't break up into pages quite nicely. But there's a way of converting a Jupyter Notebook into a presentation, into slide format, and then that prints much nicer, and then you can have separate pages in PDF. So it is possible.
Thank you. Yes.
So how is the R markdown different from normal markdown?
Markdown.
Markdown. How is it different from R markdown?
R markdown and markdown. Markdown is just the general name of the language. So R is where you have your R codes as well. You could just say curly bracket R, mean of X variable that you have defined, which will be embedded in your analysis. So R markdown is basically where you can do the analysis of your data inside the markdown catalog. Okay, but markdown is a general language. It's quite a general. You can think about it as the, I don't know if you've worked with HTML. You can think about it as an HTML operation of HTML. Thank you.
So while this is going, I'll just give a quick introduction to myself.
Yeah, sorry, thanks. I'll get your presentation.
Thanks. So my name is Thuso, and I work at a company called Zoona. I was a NASP student. I did my master's in NASP and then went on to my PhD where I dropped out and ended up getting a job in industry. So it was kind of a rocky road for the PhD. I spent 3 years kind of working on the same problem, and my advisor didn't believe what I was doing was working, so I just kind of banged my head. And then after a while, I realized I just needed to try something else and make myself a bit more marketable. So I started learning more about deep learning and machine learning techniques, and started doing some side projects, and the side projects turned on their own lives, and I created portfolios of my work and stuff like that. And my 4th year for my PhD came around, and my advisor was like, yeah, we need to have this talk. What are you going to do with your PhD? I was like, nope, that's it. I'm done. Or I got a job offer. So I went and started working at Zoona. And I started off as the first data scientist there. And we just kind of had, it was very few of us at the time. It was a brand new startup company. So it was like, we had to wear every hat. So I was thrown into being a database warehouse guy, kind of analyst guy, product manager, do everything when you're in a startup. So eventually, after a while, we hired a second guy who's sitting back there. And then from there, we started building up a team. And ever since then, I think our products have become a lot more complicated because there's a lot more people to bounce ideas off of. And also, like, being able to work in a structured team where we have people with different skill sets really makes a big difference. So don't feel bad if you drop out of school. You know, you can still be cool like me and get a sweet job. So I decided not to talk about something a little bit more corporate and how to do customer lifetime value. And so for my master's, I did X-ray counting statistics, which has a lot to do with Poisson distributions. And so when I saw this stuff, I was like, this is exactly the same thing as X-ray counting. So it was actually a really nice thing, right? And one of those ways that having a degree in math and whatever, doing some project in physics can lead on to making your company tons of money and stuff like that. So the whole point about customer lifetime is like being able to figure out how much each customer is worth. And this will help you kind of optimize how you go and target people and which consumers you'll spend more money on, or if you're spending too much money on consumers already and they're not generating enough revenue. And once you have a nice consumer CLV model, you can use this to gain insights on what's actually works for your consumers and what's controlling them, and really interrogate that. And so the couple things that we're going to be trying to predict with this model is how long will someone be an active consumer for your company? How many times will they do business with you? Because that also makes a big difference. And what will they buy and what quantity? And that can be for all different platforms. So the current way that most people do CLV is through averages. So it has a lot of assumptions that usually aren't met by businesses. So you assume, and it also doesn't allow you to have that granularity down to the individual consumer. You're just doing a broad sweep of an average revenue per person. You look at the churn rate, and this churn rate is kind of usually a number the CEO gives you. So he says, I want to know all the consumers there for 90 days. Why 90 days? Why not 30 days? No one can tell you the reason. So all these kind of things kind of come together, and you get this model, and it doesn't work very well, but everyone runs with it because that's what they've been taught to do. So the other problem can be if you don't have a subscription model. So if you sell magazines or you have cell phone contracts, like having something like this, you'll model it in a very different way than you would if you were a grocery store or were working for a doctor business or being a transactional business like Zoona is. So we have these kind of 4 quadrants of like different types of companies and different modeling regimes you need to have. So you have, like in the bottom right corner, contractual and discrete. So these are our very like magazine purchases and insurance policies where you have very fixed terms and you can pretty much guarantee regular cycles of payments. Where if you go to the continuous, you still have regular payments, but they can happen at any time. And then you have non-contractual and discrete, which like for prescription refills, that's interesting. And then I'm at our company, Zoona, is at the top left corner. So we're non-contractual continuous. So Zoona basically does over-the-counter money transfers. So we're like, we own booths, and each booth is owned by a person, and we provide the technology for these people to do their transactions. And so each one of these guys is an entrepreneur on their own. And so they manage their own business and are able to do transactions and make a living off of this stuff. But our consumers that use them can use them for any time, any way. It's like you going to an ATM. You don't really have some periods you can't go to an ATM, but you will use them whenever you need to. And you'll have different behaviors about that. So that's what we'll be talking about. And so generally what you want to do is you have some kind of, this is for one person, so you have them do something. So either buy something from you, or if you're talking about like a spacecraft, you can have their, how many times they go to space, different kind of things. And then you have this X vector, which is predicting how much the person's going to buy from you. And so what you basically want to do is try to map some kind of behavior like this, some discrete behavior like this, into some kind of function that tells you some kind of information about the individual consumer. So this is very like high level. So a little bit like a better kind of way of looking at it is you can see if we have some assumptions on how consumers react and how their churn or going out not being active with you are interacting. You can look at each transaction, which is those red dotted lines, and then kind of model how likely they are to come back to you after X amount of time. And so that's what that blue line is showing you, is the probability that they're going to come back. So as time goes along, they assume that they're not going to come back because they've lost interest. And then eventually they'll have their lifetime and do business with you, and then for whatever reason they'll go away and move to another company or not need your service anymore. And so you can see the probability kind of goes down to 0, which is what you expect after a long time. So the kind of data that we have in this kind of situation, this is not our data, so I don't think you can steal any company secrets. But it's usually just transactional. So each line in the database is just some kind of event. So someone bought something from X product and from some kind of booth or something like that. And so you get like a location, you have an ID for the consumer, that's about all you know about them. You have how much they bought for the process and the time that they did it. And so those things in yellow are all we need for this model. Everything else is kind of extra stuff that you can use later. But for this model, you don't really need it. And And as you can see, like you can see this consumer 17,850. They did a couple transactions with us and bought some stuff, but we don't know when they're going to come back and buy stuff again. So there's no indication. So this is why we need to use these kind of models that I'm going to talk about. And the other thing is, like, our consumers can also join us at any time. So there's no like one watershed event where everybody starts using us. People can start picking up at random times, and we have to be able to deal with that in this model. All we can see is from the first transaction to the current transaction that they've been with us, and we have some history about that time. But then we are stuck at our observation point, which is now, and we want to predict what's going to happen afterwards. And so what happens is we don't know if they're alive or dead. We have this uncertainty about this, and we also don't know if they're going to continue with us. So we have a problem of censoring. So we're no longer able to see the full result of this transaction or consumer history with us. So we have to use some censoring methods, which are usually found in survival analysis. So basically, that didn't come out as good. So basically, this model I'm using is called the Pareto NDV, and so it has a couple assumptions that are important when you're modeling this. So the first assumption, which is kind of blocked out by the images, is that the value of the transaction is completely independent from the rate of transactions. And we can go argue about this later, but for this model, that's what they chose to do. And it kind of makes sense. You can't really predict how much people are going to spend on stuff based on how frequent they are, at least not in ATM kind of infrastructure. Then the number of transactions given some rate and some observation time is drawn from a Poissonian distribution. So that reminds me of my history, which is really nice. And then the inactivity, which is not something you observe, it's just something you got to infer, is a latent variable now. And so we can have this parameter tau, which is just the lifetime of the consumer, and it's controlled by this factor mu, which is kind of an observed lifetime of the consumer. We can model these in any way, but for this one, I chose an exponential distribution. And then you have some period where you observe the consumer, and you want to do it in a classic machine learning way where you have your training set and your test set. And this test set is a bit difficult because the periods can be changed a lot, and you may not have a natural place to kind of bin things up. And that's all the problem with a non-contractual setting, that you don't actually know that bin and that people actually do stuff. So we can argue about how you actually do that later too. And then the nice thing about this model is you got the individual consumer level, so we can measure each consumer and give them a different number. But then it kind of filters up to a hierarchical level where we have like parameters that are working for the entire consumer base. So they're sharing information, so we have consumers and they have certain behaviors and they have a range in them. But from that, we can use that what we know about the total consumers to kind of constrain what individual consumers can do. So you have a sharing of information. And from all that, you turn that database into 3 parameters based on the time, the frequency of transaction, maybe the monetary value. And you come up with the recency, which is just the time since the last transaction, or the time from the first transaction to the last transaction. The total number of transactions they did in that period, so you just count up all those transactions, did them into that. And then the observation time, which is now, whenever you're looking. And so the recency and the observation time should be different because the consumer kind of did their last transaction at any other point, but now we're looking at the now, or at any other point too. So what do you get out of this model? Well, you get the expected number of transactions per consumer. So that's quite nice. So you can start to predict how many transactions they're going to do. And also, like, you'll see if the consumers are active and still hanging out with you guys and doing transactions, and also how long they'll be active for. So if we're going to try to predict into the future, the expected number of transactions should be kind of modified by if they're going to do business with us anymore. And then you can go and figure out the value separately. Usually I just use an average. It seems to work pretty well. And then you get your expected CLV is just a function of time or a sum of time. And you got your probability of doing a transaction given that you're live, makes sense. The probability that you're live given some parameters, mu and t. And then the probability of the value that the consumer's going to use. So you put those all together, and you got the CLV for each consumer, and you can go and tell everybody in your company that this is how much you should spend on people, no more, no less. And so what does this actually look like in the real world? So just some results from my stuff. So I got the predicted results and then the actual observed results from the whole data set. And then the black line is supposed to be if the predictions were perfect. So you can see the model kind of estimates the low number of frequency, the number of transactions, very good. And that's because we have lots of people that do very few transactions with us. But then as we go out into the kind of rare region where people are doing 20 or 30 transactions with us, it starts to kind of underestimate them. And it kind of makes sense because it's just weighting the lower transactions a lot heavier. And then we can get a kind of distribution of what's the probability of our consumers being alive. And so 0%, those guys are probably dead and never coming back to us, where you got 100% for those guys are definitely a little bit with us forever. And I think this model is actually way too optimistic for our consumer base. It's saying everybody is like 80% or above, which is kind of crazy. So that's a bit of a problem. So where can you go from here? So that's a simple model with just two parameters and a bunch of hyperparameters. So you can start adding more parameters to it and make the model more complex. So one of the things that I've been reading about that is kind of new in this field is looking at the clunkiness of transactions. So if the consumer's transactions happen once in one big full swoop, or do they kind of randomly distribute themselves across the time series, or are they kind of mid-frequency transactions? So you can have another parameter that kind of estimates this clunkiness, and this is supposed to give you lift. To me, it just seems like they're adding up the parameters, so you should have more degrees of freedom to fit your model. So it should work better. But some things you could do with the machine learning aspect on this is, so I don't really trust the probability distribution of those things. So I can come up with a holdout set and then recalibrate the probability of being alive a little bit better, so that they actually reflect more accurately of that. It's not to say that that probability of being alive is wrong. It's just I wouldn't put money on if those consumers are alive or not. But I can still use it as a ranking to see if a consumer has a high CLV and their ranking is very low on the being alive scale. Then we can kind of assign some importance to how we should act on them. Not so much as being able to figure out how many transactions they're going to do, but just as a ranking. So if we have a certain amount of budget, we can say, all right, we can spend this much. Let's get the top 1 million consumers and do stuff with them. And there is a bias that you get based on the frequency and the length of the holdout period. Obviously, we can't wait for our consumers to do a transaction over 3 or 4 years. You know, the whole world is moved by then. So you do have a weird, not a weird bias, but a pretty understandable bias that people that do shorter periods transactions will probably, you'll probably be more accurate on predicting if they're alive or not versus people that have very long periods. And then there are some places in the model where you can actually take out some of the components and start sticking in machine learning methods and even deep learning stuff. And this is something that's actually come out a lot lately. So I think there's some buzz coming up on how to combine Bayesian models and deep learning together. So I think that'll be pretty cool in the near future once people get this stuff kind of solid and it's not in alpha versions anymore. So yeah, so are there any questions? There's some resources if you want to learn more. It's a nice video from the PyData staff where they talk about this stuff and give a better explanation about what I did. But yeah, that's all for me. Okay.
Question there? Chris?
Yeah, great talk, first of all, thank you. The model you showed had some assumptions. Did you evaluate it against other models that you could potentially use? Or how did you evaluate?
Yeah, so so this guy that produces a lot of these models has like a bunch of different flavors. So the biggest changes in the assumptions are actually in the hyperparameters on how you describe the population statistics. So I played around with that a lot, mostly due to the stability of the models more than anything else. But they do have some other ways where it's like you bend them into discrete time steps, and then after you just try to do a Bernoulli trial, so you see how many successive trials you get before a failure, basically. So I haven't tried that one out, but it seems like an interesting way. And then there's some models that kind of scale from being very discrete, coin flip to being going on churn to being exponential. But it all kind of comes down to there are some known distributions that predict this pretty well. And so this WTTE RNN is kind of one of those things where they use a distribution to predict churn. So it would be nice if I had the time to kind of go through these different churn scenarios and see if they work better or not. And, you know, it's business, so you basically have a month to work on something and you got to turn it out as fast as possible. So yeah. What else? Cool.
Okay, great. Thanks. Okay, so, well, next speaker, Chris, you're going to sit up. Okay, so our next speaker is talking about computational neuroscience. It's Currin. He's busy with a PhD. I think final year
next year.
Final year next year, that's what I mean, 2018. Computational neuroscience candidate. He's from UCT and he's going to talk about thinking about thinking. So, can't wait to hear this talk.
Hey guys, I'm Chris. I have a really great background in biochemistry, psychology, and computer science, which makes no sense until I tell people I do computational neuroscience. I'm like, okay, that kind of makes sense. I also play around with AI, I do some mentoring, and I work for companies. Today I'm going to talk about computational neuroscience, how awesome it is, and thinking about thinking basically like the brain, taking time out to understand what goes on inside our heads that we use every day that ironically we don't actually know that much about. So the outline of the talk is going to be what is computational neuroscience, why should you care about it, and how can we possibly begin to understand what the brain does. Okay, disclaimer, this is biology. There isn't a single fact in biology that I know of that doesn't have an exception. And every single process in the brain has lots of other muscles, and it's not always known what aspects are important or not. Because the brain is one of the most complicated parts of complicated biology, right? So I'm going to mainly ignore complexity for this talk and err on the side of simplicity, because there are lots of concepts and we don't have a lot of time. I also don't know everything, which I learn every day. I know less and less. And then if I say theoretical neuroscience, mathematical neuroscience, mathematics, for the purpose of this talk, I'm just going to group it under computational neuroscience. But there are distinct fields, but for this, they're going to be related. Cool. So, definition of computational neuroscience is the research that involves building mathematical and computer-based models that provide a theoretical framework that encapsulates our often emerging understanding of the brain's function. Okay, so computational neuroscience is really accessible because you can just use a pen and paper where you want. Computers are used, we can do it on a home computer. Supercomputers are available like through academic resources, very easy to do. And if you get a whole bunch of books and just think a lot, you can probably actually provide a large amounts of influence in the field. Neuroscience in general is highly interdisciplinary. No matter what your background, you can actually have an impact. If you're a historian or linguist or anthropologist, all of it matters. So you can also think of computational neuroscience specifically as the art of mapping data and equations through the art of machine learning data science, right? So we want to map the data and equations of the brain because neuroscience is hard and math is easy. So I say math is easy, and no one is in uproar, which I'm kind of disappointed in mathematics is true. I say math is easy because we can often solve the equations, right? So we want to transform the complicated biological mathematical data, data into some form of mathematical equation that we can solve numerically, analytically, semi-analytically, basically somewhat more structured than just what biology gives us. And solving these equations often gives insight into what the brain does. For example, in 1968, very famous, very clean, very beautiful experiment, 1968, to researchers, Huber and Weasel, they did a bar across the cat's eye, and they recorded from its visual cortex, and they recorded the responses. And depending on the orientation of this bar, different neurons would fire at different directions. I'll probably need to spend a little more time on like the firing. But principally, they could actually start to predict that based on what orientation it was, how the neurons were going to fire. And this encoding of information was like quite a breakthrough in neuroscience. And this is in a very, very controlled environment as well. And going beyond that is incredibly more difficult. And of course, this is just encoding. You also get decoding, storage, etc. Okay. MIIA 2, very simple question. What does the brain do? I'm actually know what the brain does. It takes an input and uses output. That's what the brain does. It takes in sensory information, which, by the way, there are more than 5 senses. Bonus points if anyone can name all of them. And it produces a behavioral outcome, which can be surfing, flexing, or just orientating your eye subconsciously just a little bit to understand things better. And there's a lot of mechanical hardware, neurons, which go about processing this information. 10 to 11 neurons in just the central nervous system in order to do all this. Okay, we know what the brain does, but we struggle explaining how it works. So the brain is divided into many specialized areas. Audition, motor control, this is just inside action selection. Memory seems to work across many different areas, across many different time scales. Also, with the brain being so specialized, we actually don't notice how specialized areas of the brain are until something goes wrong. Which is an upside to motorcycles, because we learn a lot about the brain from brain damage. And the brain also has no central controller. It's highly parallel, both convergent and divergent, and in general is very difficult to understand. And this is a very high level. I'm going to go down to how the brain actually computes. The fundamental level is the neuron, the blue thing at the top. And pretty much it takes an input, I don't have a pointer, but it takes an input at the connections over here and processes that somehow, and then produces an output in the form of an action potential or a spike, whatever we call it. So the red lines there.
Chris, there's a stick there.
Stick, okay, cool, I'll use it in the future. And a whole string of these action potentials impart some information, or lack of information, because these ones are an epileptic seizure. And while we're here, neuroscience also is often an inspiration for neural networks. We see I added a basic unit there, perceptron, at the bottom. Now, the perceptron is way simpler than a neuron, and in fact, within the connection area of the neuron, the dendrites, that can be a perceptron in itself. So it gets more and more complicated, even at the input level. And then at the output level, what influences this output? Timing of the input, the type of input, is it excitatory or inhibitory? You need a balance on that. The amount of input, the location of input, structure of input, the internal properties of the neuron, and what's nearby with it. Then what does it mean when this when this output actually goes? Is it synchronized with things with neurons nearby or far apart? And what does it mean when they are? Okay, so it's slightly more complicated than just saying that it processes stuff. And this is an example of a synapse. So that's a connection between two neurons. It's called a synapse, and that in itself is incredibly complicated. It doesn't always happen either. Even though it gets a signal, it will be like, I'm just not going to release stuff now. So it's fundamental probability at the basic units of computation of the brain, the neuron. Okay, but why should you care? Why should you care about this? So I'll give you some examples of why should you care. Mainly, are these lines straight or curved? Straight? Someone's seen this before. What does it look like though? Don't tell me what it is. What does it look like? Curved. It looks curved, right? Further, I bet you some money that you don't read that whole number. You probably just skipped it. You didn't even realize I put a letter in it. Actually, I didn't, but you went back and looked into it, right? Right. So why should you care? Because the brain processes information to give us a prediction of the world. That's not always right. And further, the influence computational neuroscience can have on the world in general, also on research in neuroscience, is framing and guiding experimental research. And a very important part would be reducing the use of animals in research. Further, we can help understand diseases and disabilities. This is a very important action that someone needs to be able to do, is pick up a beer, open it. And here's a thesis with a brain-computer interface that's linked to the motor neurons. Over there, very, very sensitive, and this is an example of like a decoding algorithm, where signals are sent through the arm, and somehow the machine needs to know how to interpret that. Okay. And doing it on an individual basis is incredibly difficult because they change throughout the day, and between days there's a lot going on there, and a lot of collaboration is done and needs to be done with control theory, information theory. Further, you should also care because computational neuroscience has a huge impact and influence on AI and data science. Let me give you a more practical example of the things the brain computes and how this relates. A more real-world example, somewhat, is an example of this image, which is what can we infer from it. There's a kid riding a bike on a tar road, probably has bad parents, right? I mean, we know that even though there's a black bar covering the face, there's not a whole wheel on the right, technically. But we infer all this information from sensory information, right? So somehow these sensory information that we receive is transformed into meaningful content. But this is hard because not just the processing, but actually the sensory information is probabilistic. We are always predicting what we see and we predict how we act. But we actually don't have this throughput to handle everything in general. So the best we can do is just construct a probability distribution over what we think is happening and what we think we're going to act, and then predict how those how reaction to the environment actually can change. Further, to make things even more complicated, this is noisy. These are two neurons on the left and on the right, and there are, I don't know how many trials, 20 trials I think. Each neuron is given the same stimulus at the same point in time, over 20 trials, and they're all different, right? So that's why I say biology is difficult, because it would be nice if it worked, but or like consistently, but there's fundamentally noise in the system, and some people think this noise is inherently good, as robustness, etc. Others say we should completely eliminate it, and it's an artifact. Basically, we can model a lot of the information that does come through with information theory, but it's ultimately difficult to know what aspects of a spike train, a series of action potentials, actually carries information, even to this day. And trying to understand what the brain does with these spikes is incredibly difficult, and there's ongoing research, because spikes aren't there just to confuse experimental neuroscientists, which it often feels like they are, but the brain clearly does work, the signal does come to an end, I can have a conversation with them, right? They're not just meaningless. To be more relevant to the talk today is how neuroscience and AI can come together. There's a quote by Demi Hassaby, the CEO, I think it is, of Google DeepMind, or DeepMind these days, and he says Only by better understanding human intelligence can we hope to push the boundaries of what artificial intelligence can achieve. There's a longer quote there as well, but while you read that, I'll explain this figure as well. This is a group out of Oxford where they said, okay, this is the basic architecture of a cortical circuit, the basic architecture of an LSTM. And actually what they did is, well, let's transform this LSTM a bit to be more neuroscience inspired. How do we make it more biological, more close to what the brain does, but actually still functional enough to use in a computer? And what they did is they did a subtractive LSTM, and it reacts similar to how cortical network would react to a certain input, and they found that it's actually more efficient and more accurate on a whole host of samples and problems. I think this was published like last month, November, but you can see that these having these impacts on both neuroscience, understanding the brain, and also understanding the fundamental AI and problems in there. Other examples for neuroscience-inspired AI and why neuroscience is so important to the field of AI is these are aspects of AI that have been advanced through collaboration with neuroscience. Presently, attention, episodic memory, working memory, continual learning, like between tasks, and multiple tasks. And then in the future, what we're getting to, and what we can see touches of already, is intuitive understanding of the physical world with basically like gravity, physics, interactions, and how that comes about naturally, spontaneously, as it were. Then transfer learning, which is to try to prevent catastrophic forgetting. Then imagination and planning, which also involves some classical AI, which we revisited with more neuroscience-inspired approaches. Then also virtual brain analytics, which is basically probing what a neural network is doing in a fashion similar to how neuroscience would probe what a brain is doing. Obviously, we don't do it exactly, but we use some types of inspiration. Okay, so that's probably why you should care about computational neuroscience and how it relates to AI and data science, and why it's important to consider. So, given that, how can we actually begin to understand the brain? From going from sensory information through a network and into actually the biological implementation. I mean, if you think about it, we have cells and circuits which somehow form computations which then impart the behavior onto the world. And these behaviors and these computations actually fundamentally change over time. Or in different brain states. These are 4 brain states from people with different degrees of schizophrenia, for example. And you can see they're markedly different. But the point is they can do a whole bunch of post functionalities, like basic ones, very similarly, but yet they identify very differently as well. So one suggested approach to understand the brain is, you heard of Mars classical levels, or Mars levels of analysis. It's not that important to look at, but pretty much the bottom 3 would be computational, algorithmic, and implementation, which is to say computational level is conceptualizing a problem, and then the algorithmic level is determining an algorithm to solve said problem, and then implementation is actually building an application to do that. So you can think of action selection as a problem, and you can think of an algorithm to solve said problem, and somewhere in the brain this is done, right? And that would be like a top-down approach of saying, okay, given a certain problem, how is it implemented in the brain? Often AI starts with that algorithmic approach. Computational neuroscience says, okay, how does the brain do it as well? Or vice versa, how we think this is how the brain does it, implementation-wise, transform it into an algorithm. We actually apply it to a problem that doesn't solve that problem. That'd be another way. Then there's also included learning and meta, or development and evolution, because often learning what problem to solve is in itself a learned task. And doing it over not just now, but knowing that over lifetimes, this is an important problem to, or solution to impart, basically through genetics, which is also its own form of intelligence, right? So I'm also going to talk about just quickly bottom up and top down and differences between them. So bottom up approach to understanding the brain is let's record as much as possible from the brain, from a real neuron, sets of neurons as accurately as possible, put it into a simulation in the supercomputer, and then see what happens. Okay. Say retributively, but it accurately, to a large extent, represents certain portions or components or states of the brain, and probing those can also give some insight. But there are also limitations, of course, because I mean, we record to get the data sufficient enough to be accurate for a recording, there needs to be a lot of assumptions made as well. So there's bias in there. The approach that seems to have the most success nowadays, more recently, is the top-down route, which is what I said with the computational select problem, solve it with an algorithm, and then see if the brain actually implements that algorithm. So worry about biology a little bit later. But here's a very cool example where they built a hierarchical convolutional neural network, just a CNN, and laid it out in such a way that it was similar in architecture to how the brain would architect these visual processing streams. And what they found in this case here was that it was what they call it. They call it mappable. Image computable, mappable, and predictive. So image computable means it can actually process images that it receives, and then they give this image both to a monkey, so it's a monkey brain, the cock, and this hierarchical convolutional neural network. And what they found that is, given certain parameters, it was actually predictive of certain responses. So given this image to this network, it could predict that the monkey in that part of the brain would behave in a certain manner, which takes us back to 1968 in a certain sense. But doing it in such a way that it maps out the pathway is incredibly beautiful, and it's actually quite rare in computational neuroscience to have this mapping of a very AI-oriented network onto the brain. But this is really something that's incredibly done, and we're going to be seeing more. So it goes both ways, from top down and bottom up. Okay, just to revisit all the levels, what I really think is that computational neuroscience is focused on an algorithmic layer of understanding the brain, and I like to think that it could be the solution to understanding how we actually understand how the brain works, and not just what it does. And hopefully that is important to not just from a fundamental level of knowing who we are, but also pushing AI, pushing data science, and helping disease and components like that. So thank you for your time. If you're interested in computational neuroscience, there's a school that happens actually 50 meters away at the beginning of January each year. That started this year. So we are trying to grow computational neuroscience because we think it's an incredibly important part and can really help grow in accurate and quantitative sciences. Thanks.
Okay, any questions? Any questions? I've got a quick question, Chris. Quickly, I saw one of the books that you had there is Jeff Hawkins on intelligence and stuff. I would love to. What is your perspective on what they're doing? I know IBM looked at them as well. When I was at General Electric, they also had a look at what they're doing there. But there are obviously different perspectives. But they're trying to look at the human brain. Well, that's a very inspiring book. I read that as well.
Yeah. So what he's referring to is the company Jeff Hawkins created, Dementor.
Yep.
They created an architecture called hierarchical temporal memory.
Yep.
Hierarchical temporal memory, which is meant to be in a structure similar to how the cortex behaves. And they seem to have pretty good results with mapping onto what the brain does, but they don't have the resources in order to scale it up in a sense to actually properly compare to the architecture that we normally used to with AI.
Yeah.
So they don't seem as efficient or as robust. I know in computational, well, at least in my computational neuroscience field, we don't use these networks, at least my side.
Yeah.
So I'm sure that they definitely have a play in understanding how this works, how the brain works, but it's taking a slightly different approach.
Yeah. Any ideas on unsupervised learning from a neuroscience side? Because that's obviously a topic that needs a lot of attention. I didn't see it on the future listed specifically, but any thoughts on that? Because we need inspiration to solve that one.
Yeah, it's incredibly difficult question. What did I do to you?
I'm just curious. I forget about the people, because those are things that are important for me as well. I studied AI, so I'm super interested in this. I'm just curious because I think inspiration needs to come from exactly what you're saying. It comes to come from neuroscience.
Yeah, sure. I think I would do any disservice in trying to answer that with any degree of certainty. Basically, I'm not sure. I'm not sure how.
So what I'm thinking, I know you're doing PhD on spiking and time and on timing of spikes and stuff.
Yeah.
Isn't there something there that could potentially do? I don't know, but it just I just sense there might be something there that could be interesting. It might be a source of information that we use as humans to actually try and just figure things out. I just sense that there's something there, but
yeah, sure. I mean, the timing, just people look purely at timing.
Yeah.
Like that's it. Like looking at timing of neurons, how long a neuron is. Sometimes isn't representative of how long it takes to process, because you can have extra myelin, which speeds up this transduction of information. So incredibly difficult. There's always an exception to whatever rule that we come up with. But one of the things I'm also pursuing is inhibition in the brain and how that can impart information in certain states of the brain as well. And I think that is an area quite ignored in AI, and how, I mean, the brain has, some say, 20% of inhibition. It may not be a representative number, but the point is that it does exist, and often when we think of a neural network, we just say, well, is it 0 or higher? Over there, whereas actually you can have an inhibitory effect, and this is what, where's the paper that I showed, this one. They have an inhibitory effect here, that's why they call it tractor dust. And it seems to have improved upon the LSTM model to have better performance. So that would be my next step, to say how can we further push inhibition into the AI paradigm.
Awesome, great, thanks. Any other questions? Yep, you go.
Just following up on what you've just said about better performance.
Yeah.
What do you mean by performance? Because I mean, LSTM was not meant to mimic the brain. It was meant to be a fast computational unit that you could stack. So do you mean by performance better computational performance, or something that's just closer to what the original inspiration was, which is brain?
No, in the task, I can't remember the exact task it is now. I read the initial draft a while ago. It was more accurate on the task that they did, and it seemed to be more efficient. They could use less resources to achieve the same accuracy, or given the same resources, they achieve the better accuracy. But I would recommend, I would read the paper just to check it out. I mean, I know there's advancements, there are more, but
Maybe for a lot of some of the students, what LSTM's long short-term memory and stuff, recurrent neural nets, so it looks at time series.
Also, I was incredibly confused the first time I heard LSTM. Which one is it, long or short? It's long and like, what's long short-term memory? Why do you just call it middle? It's long and short-term.
Yeah. Awesome. Okay, I know it's getting late, so question? Yes, question?
I just want to find out, given the current campaign that's done by
Yes. Absolutely. You mean from like a purely AI perspective of trying to solve problems? So what tends to happen is, I say tends to, so in some examples what happens is people will focus on solving a problem that's important for an AI. And then they publish it, and then the neuroscience is like, yeah, we know that brain really did something similar to that. Why did you spend 2 years trying to solve an equation or a solution algorithm that was very similar to what we know already the brain does? On the other hand, what does happen as well is the AI people will come up with an algorithm solution, and then the neuroscience will be like, okay, that's really cool, it seems to solve that problem. Let's see if the brain implements some network like that. So you probe the biology of the brain to see if that architecture exists in a certain structured manner, and if it does, that could be a mechanism for it to perform that certain action. So there's definitely advancements that AI is imparting on computational neuroscience.
I would also just add to that, I would recommend, if you're into deep learning, I'm not sure if there's, but there's a very good article or blog that was by Francis Chollet, I think that's the name, on the future of deep learning. Yeah, so you guys know about it. But what was really cool, we actually look at deep learning and looking at that as geometric routines and combining that with algorithmic routines and talk about a meta layer and a kind of a library around that. And you're a bit more task focused, and you're trying to use the right routines. You construct this thing on the fly to solve particular problems, and it sounds like that could be a direction, a practical direction to go in terms of solving problems as well. But you still need inspiration in getting these smart geometric routines, algorithmic routines, and we talk about explainable AI, so we want to understand what the AI is doing. So there's so much research. We need people, a lot of people to work on this area and stuff. So yeah. Anyway, any other questions? Thinking about thinking. So we're done. So thank you.
Thanks, Chris. In closing, I'd like to thank Jacques and MIIA, and also Boubacar in his absence, and all the speakers. Thank you very much for a wonderful evening.
Thank you.